another group of mathematicians, the PDE community, started this week the same sort of seminar, the One World PDE seminar. And I think it was a good success for them. And let's see if the idea spreads even further to other groups. Let's see if one day we're going to see a One World number theory seminar or whatever. So if you have friends who might be willing to do these kind of things, please let them know. And we are also happy to answer questions of anybody if there might be questions of people willing to organize something similar. A second small comment concerning the mailing list. We told you last time to send an empty email, so no content, only a subject to this email address. So empty means really empty, because sometimes you automatically add like your address or some disclaimer of the university. So this is not empty and it's not going to work. So for some of you who did not get our email yesterday in the evening, European time, this might have been the cause. Okay, so no further words needed. We're going to start with our first speaker, Nickl.
May I add one word? There are a few people with cameras on. Could they turn their cameras off just to avoid any embarrassing situations, please? Apart from the speaker.
On top, we should also mention we're going to record the talk. So if everybody has the videos switched off, you're not going to be recorded in any sense. And if you're not interested in being on the video in the end, just don't ask a question. So we're going to continue as we did last time. So if there are questions during the talk, just put them into the chat, and perhaps we are happy again and some people are going to answer those questions. And after the talk, you can raise your hand in the participant list, and then we are going to unmute your microphone. Okay, Richard, if you're ready.
Okay, thanks very much. Can you hear me?
Good.
Can you hear me?
Yes.
Yes, all good, all good.
Okay, fantastic. Okay, well, thanks so much for asking me to do this. I'm very happy to do this, and it's a great interface to get to speak to each other. I guess this is a probability seminar, and I'm more of a mathematical statistician, but maybe we can find some common ground anyway. So I will talk about statistical versions of Calderon problems. This is joint work with a former PhD student of mine, Kweku Abraham, who is now a postdoc in Paris, Orsay. And the paper is also on the archive, as you can see here. And that's Kweku still in St. John's College Library, I think, in Cambridge. So let me just see if my highlight works. So you can see yeah, that does work. So you can see the archive submission here. Right, so I'll be writing on the slides like this. I hope people can follow. Okay, so, well, I guess I have to undo it now. Okay, and this also, just one second. Okay, so what is this talk all about? There's sort of two aspects to the story. One is more coming from sort of inverse problems with partial differential equations, and the other one is coming from real medical imaging applications. You can see one of these instances sort of here in the picture. You would you want to kind of have a non-invasive imaging device that wants to find out maybe if something inside in the lung here has happened or not, and you want to do this obviously without cutting up the body. So one way, there are many ways to do that. One way to do this is to attach certain electrodes to the patient and sort of apply a voltage on all of these electrodes, and then measure also on all of the other electrodes what sort of the output is as the voltage sort of propagates through the body. So the physics of these are just the physics of electrostatics. So actually the way this voltage will propagate through the body follows a partial differential equation, particularly an elliptic one, which I've given here down there. So you could think of it just over here, a standard elliptic second order PDE with a conductivity coefficient gamma in here. And you sort of apply a voltage on the right hand side, so that would be your psi function, that is sort of the boundary information that you feed in. and you want to maybe decide whether you can reconstruct this gamma function also in the interior, where the lung sort of inside the body is, from boundary informations exclusively. Okay, so if you think of this again, so you would have some sort of medium that you're trying to image, and you would apply electrodes all around this medium, like in this picture, and then you move the electrodes sort of just in a clockwise fashion, and you could model each of these sort of portions of the boundary of my domain by this psi p function that you have up there, which is just an indicator of the set, which is sort of a part of the boundary. Yeah? So if you want to write this mathematically, what you would measure is the current flux that sort of emanates at the other side of your domain once you've applied your voltage. So if you think of this would be an average measurement over the area of each electrode. Let me just try to get this highlighter again. So you see this here, this would be sort of an integral where lambda gamma is the operator that we'll be concerned with in this talk, which is sort of the map that sends the boundary information of your elliptic PD sort of to what you see on the other side. And of course, since this is an integral, you will just have an integral over the whole region IQ when you apply the voltage at the region IP. So your data somehow is kind of matrix form for each of the electrodes. You can either apply a voltage or record the current flux. And so the current flux, what is it? It is actually the Neumann data of this PD. So you observe the gradient of the solution of this elliptic PD given the right-hand side, and then you just take the directional derivative for the outward normal. Okay, so this is sort of the main setting, and of course, if you can imagine, if you do this in physical practice, you will have some statistical noise. So there will be some random statistical error that occurs every time you make such a measurement. But before we discuss that, we need to investigate whether this problem is at all ill-posed. Is it in principle possible to reconstruct the interior conductivity gamma from making sort of a bunch of these boundary measurements? Okay, I don't know if there are any questions. I guess you know the rules how to interrupt. But so the question really is, can we determine this conductivity that describes the particular second order elliptic differential operator from such boundary measurements involving this operator lambda gamma? Note that the operator lambda gamma itself is a linear solution operator of an elliptic PD. So it just sends some right-hand side into sort of another solution in a linear way. But the mapping that assigns the unknown conductivity gamma to this Dirichlet-Neumann map, so this lambda gamma operator, that is in itself non-linear. So you cannot expect that you can just go back sort of by a trivial linear inversion formula. So this is, in other words, a non-linear inverse problem. Yeah? So the data that you get depends in a non-linear fashion on the underlying parameter gamma that you're trying to find. So actually, if you study this just from a pure mathematics perspective, you can just ask, is this map that sends the conductivity gamma into lambda gamma injective? If it is injective, then it tells me that in principle, I can sort of discriminate what gamma is based on the data. And this was first posed by Alberto Calderon in 1980, so a while ago, and then solved in the affirmative in a sequence of quite influential papers in sort of inverse problems theory by Sylvester and Ullmann originally, when the domain on which your elliptic PD is sort of set is three-dimensional or higher, and the two-dimensional case is sort of special and in some sense more difficult, was proved by Nachman later in dimension 2. There also are in principle some reconstruction formulas that follow from this theory, but they require exact knowledge of the operator, and they cannot really deal with the typical issues that one has when one wants to do this in practice, which is numerical approximation and dealing with statistical noise. And of course, also coming up with a good experiment that allows you to do these measurements. So these papers are very much kind of pure mathematics papers. There were these three up there. I think they were all published in the Annals of Mathematics, so they're very nice results in mathematics, but they don't give you a way to solve the statistical problem at all. Okay, and if you want to read up on the background from the more mathematical perspective, there's a very nice survey paper by Ullmann in 2009, and also some very nice lecture notes by Mikko Salo on the Calderon problem that you can just find them online. Okay, so yes, the map is injective, but how do we deal with statistical noise? Well, and how do we deal with real world experiments? Well, somehow here you have to discuss, as always, when you do statistical inverse problems, carefully the measurement model that you might want to consider. The first one, so I'll talk you through three measurement models. And we'll sort of try to argue why they are closely related in the end, and then we'll prove some theorems in one of them, and I'll explain how they relate to the other models as well. The first model is the one that I had sort of introduced at the beginning, which is this electrode model that one uses in electrical impedance tomography, as this kind of medical imaging device that I mentioned earlier is called. And what you would do there, you would take somehow a partition of your boundary of your domain, which here I've written partial M, but actually this should be partial D. Apologies for that. So this one here should be just partial D. And so you take these indicators, you take them orthonormal, say for the standard L2 in a product on the boundary manifold. And then you apply this lambda gamma operator, which is the solution operator of your elliptic PD, and then you take the Neumann data from that solution for one of these points on the side. And you would expect that then when you make a measurement at any of the other electrodes of what the current flux is, that you incur some noise. And we will model the noise as is common in statistics. You know, if you have a superposition of many independent measurement errors that you model in a stochastic way, then approximately it is sensible to assume that this noise is Gaussian. And so we assume that each time we make such a measurement, we have a certain standard normal measurement error scaled by some noise level that I will call epsilon. And you make, you know, you try to make as many measurements as possible, of course. So the number capital P, which is sort of here, will sort of denote the number of measurements. Okay, that is the model I introduced at the beginning. And you can see that this model somehow is a matrix data model, because you sort of have double index P and Q, where sort of in one entry you have the Dirichlet-Neumann map applied to your indicator function, and then you integrate it against one of the other indicator functions. Okay, so that is the electrode model. That is possibly the most realistic model. It is also, from a theory point of view, a bit more difficult, although we'll see that one can deal with it. The next model would be the following, where, well, basically what happens here is just instead of these indicator functions, you're just going to take other functions that are orthonormal in L2 of the boundary manifold partial D, which of course, you know, if you think of applications, if you do this like with a ball, then the boundary manifold will be the sphere. And so you could, for instance, then take as an orthonormal basis just the standard spherical harmonics. If you're on the disk, you could just take the standard trigonometric polynomials, and then on a general boundary manifold, you can take eigenfunctions of the Laplace-Beltrami operator, and then sort of basically just measure those matrix data, where you apply again the Dirichlet-Neumann map here to the phi k R functions. So these eigenfunctions, of course, they give you a simultaneous basis of all Sobolev spaces on the boundary manifold, so you can normalize them as you wish. This is what the parameter R sort of models, it's most natural, perhaps, again, to take it orthonormal just in standard L2, or there sometimes it makes sense to have it orthonormal in H1. Okay, and this is what we'll call the spectral measurement models, because you take sort of the spectral data. Okay, and again, every time you make a measurement, we assume that you have some Gaussian noise. Now, this is already in that model. You could imagine that you make many measurements. You let capital K, the number of measurements, grow quickly, and there's some sort of an idealized continuous measurement model that corresponds to letting K, capital K here, really go to infinity, which is something that one could call the white noise model. So I've drawn a white noise at the bottom here, but what it means in this case, you just regard lambda gamma. Where's the spotlight? Just give me 1 second, highlighter. You regard lambda gamma as an operator in a space of Hilbert-Schmidt operators, and then you add a Gaussian white noise at a certain noise level epsilon, which is a white noise in the Hilbert space of Hilbert-Schmidt operators. So this is somehow very literally what happens when you take a limit of the discrete spectral model and let K go to infinity. And you can somehow make this this equivalence also rigorous, and I'll discuss this a little bit, but formally, this is sort of in the continuous world. This is, of course, when you do PDEs, sometimes attractive to write theorems in, and so we'll initially develop the theory in this model, and I'll explain how to carry it over to some other settings. Yeah? So we need to also some notation. This Hilbert-Schmidt, this space of Hilbert-Schmidt operators between the Sobolev space HR and L2 just has this natural sort of summability condition, and sort of this is a space that somehow pops up naturally. I think this is also, when you look at the inverse problems literature, it is very clear what the lambda gamma operator should be. It is a bit less clear when you take a continuous formulation of the model what the noise should be, and somehow it's important to understand that the noise really is the appropriate sort of notion of noise is one in this space of Hilbert-Schmidt operators, which is a pretty rough random object, and much less regular than the noise is often assumed to be in the literature on inverse problems. Okay, so these are the three statistical models that one can have in mind. I don't know if there are any questions so far about these measurement models. I'm gonna otherwise give just
Richard, I think because of the nature of the seminar, we'll save the questions at the end. We'll field questions.
Okay, okay, fine. Yeah. Sorry, I didn't catch that. Okay, so these are the three models. Let me just give you a quick summary of what kind of the theorems are that we're going to obtain, and then I will try to introduce them a bit more concisely. So the aim, of course, is can we find an algorithm or some, some rule, some decision rule based on the data that we will call gamma hat, which recovers gamma, sort of the unknown interior conductivity, at some rate of convergence. We could, let's call this rate of convergence R epsilon. And let's, assume that we take more and more measurements, or somehow in the white noise model, we just let the noise level epsilon go to 0. And of course, ideally, you also want to have a concrete algorithm that you could use computationally, because of course, this is a nonlinear inverse problem. So it's not so clear actually what we're going to do at any rate. So that is sort of the game in town. We want to characterize this rate. Actually, we'll prove things in the continuous model, and then argue that there's this notion in statistics which is called the Lecam equivalence of statistical experiments, which allows you to define a notion of distance on statistical experiments, that if you can make that distance somehow small, this tells you that all the information theoretic properties like optimal convergence rates that you could obtain or so are the same in any of these models. And we'll show that effectively these three models that I have introduced are really more or less in some sense very closely related to each other, at least in the small noise limit. Yeah? So you can somehow try to prove your theorems in one of them, and then there will be a way to transfer them to the other models. So that is one of the results we obtain, which is already interesting, that particular the electrode model with these indicators actually somehow allows you to compare yourself directly to the continuous model. But then, of course, once you have that, the question is, what are the recovery rates? What is sort of the guarantees? What are the guarantees that we can get in this case? And we'll characterize not just the rate that some estimator obtains, but we'll give a complete picture of the information theoretic complexity of this problem. So we'll obtain rates, and we'll show that these rates are the best, not just for the particular algorithm that I will introduce, but for any algorithm that you could ever come up with. Yeah? So and the rates are logarithmic in the noise level. So they are basically up to a power delta that one can discuss what it is, which is in the red display, logarithmic in 1 over the noise level. So as the noise level goes to 0, you will have, you might initially think, you might not like it. Maybe you find logarithmic too slow. But of course, it depends on what your noise level is in the end. But the way I've set up this problem, if you assume that the true conductivity is H alpha regular, so lies in some H alpha Sobolev space, and so is somehow a smooth enough function, then this is the rate that you will get. So in some sense, the rest of the talk now is to try to convince you that there is a meaningful statistical algorithm that attains this rate that can also be implemented. And the second part will be to understand why no better rate than logarithmic can be obtained in this nonlinear inverse problem. Yeah, and you see that this, of course, gives you somehow more information than the mere injectivity result that has been given by the pure mathematicians, because injective, doesn't tell you something about the modulus of continuity in your recovery problem, particularly if you have noise. So I think one does learn something of that, particularly when you compare it to other inverse problems that I will discuss at the end if I have time. Okay, so this is sort of the roadmap, just very heuristically. Let's look at the upper bounds, like at the constructive part of the story. How would I try to estimate things? Well, if you're a statistician, somehow the first thing that you might want to do before you even turn your brain on is just what people have been doing since Gauss in the early 19th century, is just to do some kind of least squares fit. So you take some least squares criterion, and you just try to find the output of, the parameter that is most likely to have produced the output that you have. So if you look at this in this equation here, so you see I just take my matrix data YKJ, and then, let's say we're in the spectral model. I mean, the main ideas don't really change. I just see if I had chosen gamma here, what is sort of the output that I would have generated for this particular lambda gamma, and some sort of the Hilbert-Schmidt distance, which is some sort of a natural least squares criterion here, because it has to do with the log likelihood function. And I would then look at the square distance and maybe put some penalty, because obviously our model for gamma will be an infinite dimensional model. There's no reason why I should make any constraints. So it should be some Sobolev function. But of course, if you take arbitrary Sobolev functions, you can somehow get a fit as good as you like. And so the question is, what penalty are we going to do? Well, I guess a natural penalty often used. You can do a lot of different choices, but would be just to penalize the Sobolev norm, for instance. Yeah? If you do something like that in the inverse problems literature, is sometimes called Tikhonov regularizer. Now, you could do that in this electrical impedance tomography story, but it doesn't quite make sense to just penalize gamma as such. You need to enforce ellipticity. You want the gamma to be strictly positive, because obviously if it is not, then the differential operator is not elliptic any longer. So you want to somehow enforce that constructively, because also in the physical experiment it is going to be the case. But this is easy. You can just, maybe take a little constant m and just add an exponential, like transform whatever your original parameter is and exponentiate it, and then you will always have something positive that is bigger than m. In fact, taking the exponential function for this theory is not always the best thing. It's better to take something that is a bit tamer at infinity, but in a nutshell, that's kind of the right idea. Okay, so you can do that easily, but even if you do that, it's not clear how you're going to optimize this thing, because the theory of convex optimization that allows you to optimize these things even in very high dimensional situation requires this functional to be convex. And it is not, because even though, of course, the sum of squares there is convex, because of the non-linearity of this map, this is not convex at all. So if you run some convex optimization algorithm on that, you may very easily get stuck in a local optimum, and then you don't know that you're recovering anything at all. Okay, so in some sense, maybe you don't want to do that really, and people don't do it in inverse problems. They prefer to do something different from optimization, which is somehow the Bayesian approach to inverse problems that was sort of famously advocated by Andrew Stewart about 10 years ago in an influential paper, and has sort of boomed in sort of this applied PD intersection statistics, intersection uncertainty quantification area. The idea is actually that you take your parameter capital F, maybe you have to make it a positive conductivity again by some link function, but that you can do it easily. But you model fundamentally the underlying parameter by a Gaussian process prior. So you pick a random function on your domain in Euclidean space that arises from some Gaussian process. We'll discuss choices of those in a moment. And then you just use Bayes' theorem to give you a posterior distribution on function space, which you can see here how that works. Obviously, that's just we know how this should work. You will get somehow a penalized version, a reweighted version of the log likelihood, where L of F is the log likelihood, and the penalty in an infinite dimensional Gaussian process setting that you're going to put there somehow very hand wavy for the moment will be the so-called reproducing kernel Hilbert space norm squared of your process. Yeah? So if you take a Brownian motion, then your reproducing kernel Hilbert space would be H1, and then you can play similar games with Gaussian random processes in higher than when you model random fields that are indexed by, say, a Euclidean domain. Okay, now if you then write out what this is, this posterior measure in our case, it looks all a bit circular and like emperor's new clothes, because actually the penalized likelihood surface is exactly the criterion function that we tried to optimize on the previous slide when we're trying to do penalized least squares. So it seems, you're going to just write down the likelihood, which is what I've written down here, and you put some penalty, and somehow the choice of Gaussian process prior gives you the way you penalize in your model. So if you, for instance, try to find the maximum a posteriori estimate in your model, then you will just try to do the same optimization exercise as before, and you will not get anywhere. But of course, once you have the Bayesian interpretation, you can do other things than optimization. So let me just quickly draw here. So fundamentally, the problem is as follows: that maybe your penalized likelihood surface looks like this, yeah? And so if you try to optimize this function, so the maximum will be here, but if you take an iterative procedure in high dimensions, you might come from this side, and then you will get stuck here because you will not go down in this well if you optimize. But you could, instead of trying to find the maximum of this functional, you could try to find its average, its mean, yeah? Which might also not really be here at all. The mean might be maybe somewhere here. But you can compute it by ideally some MCMC method that allows you to compute an average of some measure. Okay, so it is fundamentally not an algorithm of variational flavor. It is an averaging approach. So of course, I'll describe how to do this in practice in a moment. But of course, the question is, if I do, okay, I accept that I can't find the optimizer, I might get stuck here. But then I want to do the mean, but in this picture, for instance, the mean might be somewhere where the likelihood surface is possibly not very high. So the question, of course, is it any good, this posterior mean? And I'll try to prove some theorems that tell you that actually, yes, it is good, but you have to do very different things from the things that people usually do when they analyze optimization-based algorithms. Okay, so just to think about this algorithm that people are using and that is kind of very popular in MCMC, and this is just a vanilla Bayes algorithm. You can do much more complicated things. It's a so-called PCN algorithm, which was invented by, well, it wasn't invented, but advocated in the inverse problem setting in this paper by Cotter, Stewart, Roberts, and White. It's very nice. So you have your Gaussian process prior, so you draw a random function from your prior. You can do that in high dimensions. This is a fairly cheap thing. And then, just like in an iterative method, you make a proposal. So you kind of, you compute this, you initialize somewhere and you compute a proposal, which is just these convex combinations. So you start at F0, then you draw from your Gaussian, you make a step according to this kind of Gaussian convex combination that we have here. And then you either accept or reject the proposal, and you have some sort of Metropolis Hastings correction, which is basically looking at the likelihood ratio test between your initial point and your new proposed point. Yeah? So if you think of it in this picture, you know, you will, if you go somewhere up, you will always more likely accept it in your proposal. But when you take something for which the likelihood ratio here is actually less than 1, which means that your proposal is actually worse and you would be coming down this well here, then you still accept it with some probability. And of course, in this way, the Markov chain explores the whole surface eventually and sort of wanders around and around, and it allows you eventually to go to find the average of the function without the problem of getting stuck at some local optimum, which in this non-linear setting is very important. Okay, so if I now erase this picture, then I can kind of give you some theory for this algorithm here, which has been analyzed. So you can show that this gives you a Markov chain. It's not difficult at all. And there's a nice paper by Martin Heyer, Andrew Stewart, and Sebastian Former a few years ago in the Annals of Applied Probability, where they prove non-asymptotic mixing time of this process towards the posterior distribution that you're trying to sample from, that you're trying to compute the average from, under conditions that do not require convexity if you want log concavity of the posterior measure. And there are other MCMC algorithms that can get away without convexity too. So fundamentally, these algorithms allow you to sample from high dimensional measures that are not log concave, which precisely for this nonlinear inverse problem with the Cardagon problem is something that you will have to do. Okay, so now, of course, this allows you to compute this posterior mean, but now I go back to the question I asked before, is this posterior mean actually any good? Should statisticians want to compute it? So here are some examples from typical Gaussian process priors, just to convince you, if you wanted to implement this, you can, for instance, use these Matern processes that allow you to realize a Sobolev space of any degree alpha as the reproducing kernel Hilbert space, which then sort of gives you the penalization in your algorithm. Okay, so and my question now is somehow, what are the guarantees one can give for such algorithms? Okay, so I'll give you now an upper bound for this Bayesian solution of the Cardagon problem, and then we'll investigate how to prove that and maybe discuss some lower bounds. We should still have some time for that. Yeah. So I will initially prove everything in the Gaussian white noise model 3, this continuous model. I mean, I will not prove anything here, of course, but that's how we did it in the paper. And then we discuss how to do it in the more general case. So the prior you're going to take is in principle one of these Gaussian random fields indexed by your domain D. However, we'll kind of do two tricks or two little tweaks to it. The first is we will let it live on a compact subset of the domain. So we will assume that gamma is basically known outside of some compact set, and this is accommodated in this psi function here, or a zeta function here that sort of cutoffs everything outside of a fixed set. But that's not really a big loss of generality. And the other thing is we shrink this prior somehow in a way that depends on the noise level. So this means in the language of inverse problems that we penalize a bit more, because it kind of amplifies the reproducing kernel Hilbert space norm. So it means that the way you penalize shouldn't be completely ignorant of the noise level. Rather, you should somehow scale it with the noise level. But this is something that you can always do, and somehow almost doesn't, it doesn't really hurt you. Non-asymptotically also not. Okay, so here's the theorem that we prove for the algorithm, which is really the posterior mean that you can sample from with convergence guarantees coming from applied probability. Yeah, so this is not just some algorithm that one can write down and not compute. It is something that is provably computable. And in fact, here is a statistical guarantee for the convergence of the recovery that this posterior measure, this posterior distribution somehow outputs miraculously after your MCMC for the interior conductivity after having only observed the Dirichlet-Neumann map of this PDE, so just this boundary information. And we can indeed prove, if you take your posterior mean, so the posterior mean sampling is F bar, is on the level of the capital F, and then you just apply the link function to make it positive, because the MCMC algorithm, of course, has to live in a linear space. So this can only operate on, say, RD or L2 or something. And then you make the conductivity afterwards from applying phi to it. But if you do this, then you will get, for this kind of conductivity that comes from the posterior mean, a convergence rate bound of this kind. Yeah? So it is logarithmic, as I've said before, and you will need some regularity. So particularly you need the conductivity to be H alpha for some alpha large enough, larger 3 than dimension, for instance, where D is the dimension of the domain capital D. And this result, as we prove in the paper, holds in fact also in the other 2 models. So it holds in the electrode and in the spectral measurement model. Okay, so this is the main upper bound, which tells you that this problem does have a solution at this convergence rate. And it is, you know, sort of reassuring that this kind of magic trick of using a posterior distribution, which uses no structure of the inverse problem at all, really, does actually solve this nonlinear inverse problem successfully. Okay, and this result also holds in the other 2 measurement models if the number P of electrodes or the number K of spectral measurements that you make is large enough compared to 1 over epsilon. So obviously P and K will have to grow, say, polynomially in the noise level. So that is the first main theorem. Before I talk about the lower bound, just a few words about the proof. Because it is not completely obvious that something like this works. Yeah. So there's a well-established theory on sort of Bayesian non-parametric methods that tells you how Bayes methods fare in infinite dimensional statistical models. That was invented largely by Art van der Waart in Leiden in Holland with co-authors, several co-authors over the last probably like 20 years. And this tells you somehow that yes, posterior inference, if you use a posterior in infinite dimensional setting, it kind of does work. There has been work before by Diaconis and Friedman that said that Bayes methods don't work, but in a way, this was not really telling the whole story. And now we have a much better understanding. And it will tell you in the model in which you are, in the natural information distance, say the Hellinger distance of your model, you will get some consistency. You will get some convergence rates of the posterior measure. Now, in this inverse problem, however, this nice distance in which things are good for you here, this Hellinger distance, is actually not at all the distance you're interested in, because it looks only at the distance between sort of the forward data, between the Dirichlet-Neumann map for gamma and the Dirichlet-Neumann map for lambda gamma, but really you're interested in getting gamma, so you want to go back. So in some sense, even though there is some consistency, some convergence rate, it is somehow in a distance that is too weak for you. It doesn't really tell you what happens at the gamma level. So even though you're going to use this at the beginning, you might have to think a bit more on how to go further. And even this theory is usually developed for priors that are Gaussian on the regression function, on the thing you're actually sampling from. But in our case, of course, we start with a Gaussian process for F, but then you filter it through this PDE map. So actually the prior on the lambda gammas is not Gaussian at all any longer, because it is a nonlinear map that comes from some PDE. So this prior is a very strange one from a statistical point of view, but it is the one that you have to deal with if you want to use these convergence guarantees by the Heyrer-Stewart-Former paper. But of course, now you can start to do some PDE theory. You can somehow understand the modulus of continuity of this PDE forward map that comes from the Dirichlet-Neumann map. And there are some Lipschitz estimates for this forward map. In some norm, well, you have to put the L infinity norm on the Fs, and then you have to put some particular star norm on the operator you observe, which is this operator norm between h1/2 and h-1/2. And there is also, importantly, a stability estimate, which goes back originally to Alessandrini and then also Novikov and Santa Cesaria, of this kind, that allows you to say that you can actually control the distance on the gammas by the implied distance on the operator, but the modulus of continuity of this inverse map is really only logarithmic. Yeah, and then of course, you know, if you start to think whether this is optimal or not, you might already expect that you will not get something better than logarithmic overall. But at the level of the PDE estimate, that's just a stability estimate, so it doesn't tell you anything about the statistical performance. But if you put this together and study infinite dimensional Gaussian measures carefully, then you can you know, make this work. So let me actually, I forgot to say, so this star norm, which is crucial from the PDE story for the Calderon problem, goes between the h1/2 Sobolev space and the h-1/2 Sobolev space. But the statistical distance on the lambda gammas is a quite different one, because it is, as I've said, this Hilbert-Schmidt distance. So the Hilbert-Schmidt distance on these operators, of course, is very different in principle in an infinite dimensional setting from this operator norm. Yeah, so they're between different spaces, and then also one is a kind of L2 distance, and the other one is a subnorm distance on operators. So something doesn't really connect in some sense. But one of the key steps in our proof is the following lemma, where we somehow control this in a two-sided way, at least locally. So if you already localized, and you can show that for the prior we have, you can already localize on a fixed, say, bounded set of gammas, you can actually, of lambda gammas, you can actually compare these distances, at least up to losing a square root. And the reason behind this, okay, there's some PDE theory that allows you to say that these lambda gamma maps are somehow infinitely smoothing in a certain Sobolev sense, and then you can construct a suitable low rank approximation of lambda gamma from a low dimensional space where these norms are approximately equivalent, and then you sort of pass this to the limit in a clever way, and you get these inequalities. So what these inequalities tell you that the information theoretic distance, like the Hellinger distance that matters to the statistician, is somehow compatible. So this is the distance that matters to the statistician, and this is the distance that matters to the PDE people, and they are somehow up to maybe losing a square root fundamentally compatible. I don't know if this estimate is sharp, but for us it is good enough, because in the end you're going to take logarithms anyway, and they take out these powers that you have. And from this you can then get some contraction rate. You can show that the whole posterior measure on the capital F's actually, which are sort of the real gammas up to the link function, contracts at the rate that is dictated by the stability estimate, and so you get the overall result. And you still have to prove, you have to work a bit harder to show that the posterior mean is actually as good as the posterior measure, because of course the measure is just a convergence in probability, and you have to give a kind of high dimensional non-asymptotic version of a uniform integrability argument here to pass from the posterior contraction to the posterior mean. So I think I have maybe a few more minutes. Is that right? Or okay, so just 2 more slides. So let's talk a bit about the lower. Say again?
Good for time.
Okay, so let's talk a bit about the lower bound, because obviously, you know, initially you get these logarithmic rates, and then you wonder, well, that's not great. I mean, there's a bit of a folklore in the Calderon problem that it is indeed severely ill-posed. So, you know, like it's hard, whatever that means. But from a statistical point of view, of course, okay, it's nice to show that your posterior mean has this convergence rate, but obviously you want to know whether the rate is sharp. Is it really necessary to get logarithmic rates in these measurement models? And well, we did prove that also, which is this theorem. I mean, we proved this for a prototypical case where you just work with balls as your domain. So that kind of, you know, you have some big domain, which is just a unit ball in Euclidean space. And then you assume your conductivity is 1, except outside of this subdomain. So this is sort of a condition that matches what we have in the upper bound, at least in a special case. So you could imagine that this is prototypical. And then you assume that, you know, you have some, you know, alpha has to be at least 2, so a smooth enough, Sobolev, in a Sobolev sense, smooth enough conductivity. And then you can prove the following, which is not a lower bound for the particular estimate that we have. It is a lower bound for any measurable decision rule that you can construct from your data in the white noise model. And then I will argue that this holds in the other models as well, where you get this rate. So you take the infimum over any reconstruction rule, any measurable function of the data, And then you look at the worst case risk, which is something we call minimax risk, over a Sobolev ball. And of course, you kind of want the conductivities to be bounded away from some m, from below by some m. And then the probability of having an error of at least a constant times log 1 over epsilon minus delta prime. I'll discuss delta prime in a moment, but this is at least lower bounded by a quarter. So there's a information theoretic barrier for getting a recovery in the statistical Cardagon problem at a rate that is better than log of 1 over epsilon. And this basically matches our lower bound up to the value of this delta prime. This has to do, I mean, I'll discuss the proof in a moment, but this is kind of a delicate PD question, what the right delta prime delta is in the, somehow the stability estimates that underpin this, and or maybe the instability estimates rather for the lower bound. And you know, we didn't dig into this because it gets pretty difficult. It was already pretty technical already, but for us, what mattered was to show that logarithmic rates are indeed necessary here. And so, you know, it tells you fundamentally that the statistical Cardagon problem is severely ill-posed in the sense of logarithmic rates, and that the rates that we got for the Bayes procedure were sort of the natural Bayes procedure, which just looks at the data and the prior and the likelihood and doesn't look at the inverse problem specifically, actually gets these optimal rates. So there's no innate suboptimality of using the Bayes method, which of course is also computable. And this lower bound holds as well in both of the other models. Because you can imagine that this white noise model, well, let me talk a bit about the proofs of the lower bound in the last 2 minutes. So there are 4 steps in the lower bound. One is an exponential instability result for a sort of related Schrödinger equation that kind of is closely connected to the Cardagon problem, which was given by, in a paper by Mandace, in 2001. And then again, for the statistical information geometry of your model, you have to compute information distances in these Hilbert-Schmidt norms between these spaces. So that's what matters for the statistician. But the comparison inequalities between this information distance and the operator norm that I mentioned before, we already proved them. And then once you have these comparison inequalities, then you can use sort of standard machinery from non-parametric minimax lower bounds to get these results. And so I think that, yeah, and so once you have the lower bound in a white noise model, you kind of realize that any of these discrete models, both the spectral model and the electrode model, can be somehow realized as projections of the continuous model. So if you prove the lower bound in the continuous model, then also you get the lower bound in any of these models. So fundamentally, in all these 3 models, the rates are logarithmic, unless, of course, you were somehow willing to assume that your conductivities are not smooth. I mean, you could maybe make your life not easier, but kind of you make it more difficult, but in some sense different, by assuming not that your conductivities are smooth, but maybe they're piecewise constant on very nice sets, and then the theory could be different. There could be different stability estimates as well. But if you believe that your conductivity has some classical Sobolev regularity, then this is indeed, in a rigorous information theoretic sense, a logarithmically ill-posed problem. And so just to wrap up the last few conclusions, I would like to say that these logarithmic rates, you know, I think it's very nice to prove that Bayes methods pick this up, that you can give a Bayesian solution of the Cardagon problem. There's somehow one thing that one can think about is what would happen if I could measure in the interior of sort of the body, if I can do kind of invasive tomography instead of non-invasive tomography. And there are 2 recent papers that I mentioned here that in this case, the minimax rates, the statistical rates start to be polynomial in the noise levels. You can suddenly get much faster rates. And so in a way, the hardness of the Cardagon problem really comes, maybe not surprisingly, from the fact that you only take boundary measurements. And now just boundary measurements as such is also not the whole story, because you can cook up other boundary measurement models, such as with X-ray tomography, where also the rates can be faster. But of course, in these X-ray tomography cases, somehow you don't have elliptic PD, it's more like a transport PD. So in some sense, this electrostatic measurement model that you use when you do electrical impedance tomography, in some sense produces bad statistical convergence rates. And therefore, from an information theoretic point of view, we have a rigorous way of saying that it is somehow harder or produces less precise imaging modalities, if you want, than sort of maybe other settings. So you can imagine there are lots of these nonlinear inverse problems, and one can sort of start to compare things. Bayes methods typically work pretty well, and also in the Cardagon problem. But it's certainly of interest to try to maybe investigate further, and particularly cook up some models where for the Cardagon problem one could get perhaps faster rates, but this will not be along the lines of requiring sort of Sobolev regularity conditions on the conductivities. Okay, I think I'll stop here. Thanks for your attention.
Okay.
Thank you very much, Richard. So now I'm starting with one question from the chat. So there's another one. Other people might go into the participant window, and there's a button to raise hands, and then you will see a blue raised hands, and we're going to turn on your microphone. But we might start with the two questions from the chat. So Richard, you might also see them. One is from the physics point of view, noise is indeed Gaussian. Appeared to talk.
So the question is whether the noise is Gaussian?
Yes.
Well, I mean, let me just go to the model. I mean, for us, this is an assumption. I think if you think what you do when you do the electrode measurement, the body will move around a little bit, that the electrode wiggles a little bit. So you have a superposition, you're adding up many small independent errors when you do an experiment. So that in itself can be modeled by a Gaussian, just by the central limit theorem, which tells you that a sum of independent things is approximately normal. As the voltage propagates sort of through the medium, again, I mean, there's no reason why noise should be anything specifically different from Gaussian. So it is certainly, at any rate, an approximate measurement model that will make sense, as in most of statistical regression models of this kind.
So we have another question from Pascal. Is anything known on statistical information threshold for this problem?
Statistical? Can you just repeat the question?
Statistical threshold information. A statistical informational threshold. Oh, everybody's still
some of which you cannot deduce anything on the gamma, and below which you can deduce something on the gamma.
Okay, I understand the question. So noise level epsilon, when you take discrete measurements, then the number of electrodes P or the number of spectral measurements K that you take has to be large enough compared to the sort of inverse noise level for you to get recovery. So indeed, in some sense, you could try to calculate what this relationship is precisely. Our theorem just says that P and K has to grow large enough compared to something we can quantify, but we did not attempt to find the optimal sort of or minimal growth of P and K compared to noise level epsilon that you need to recover gamma. So I think it is an interesting question in the discrete model. In the continuous model, by nature of the continuous model, there is no restriction on epsilon at all.
Pascal seems to be satisfied. Any other questions?
I have a question, if the chair is permitted.
Go ahead.
So my question, Richard, is, so you're, if you have a situation where what you're scanning is, for example, suppose you're scanning a brain, so you have the skull positioned rather carefully inside of the machine, and you know roughly that the temple lobes have to be, say, against some pins or something like that. So you have a point of data assimilation there where you know a little bit more about what it is inside the scanning machine. So in a way, you're constraining what you see on the boundary against some fixed points. So some kind of data assimilation. So if you threw that into the model, would that just make it crazy, or yeah?
I mean, in principle, if I understand the question correctly, you would. I mean, if you have some geometric information about the skull that you're scanning,
yes.
you could just use this and put it into your choice of domain, capital D.
Mm-hmm.
So in principle, you can put the geometry of the domain in your choice of the domain. Of course, if you want to make measurements, if you want to then compute the eigenfunctions of the Laplace-Beltrami on a kind of weird, funny domain, this becomes numerically much more expensive. Because you have to compute, it's not the standard spherical harmonics any longer or so. But I think from a theoretical...
So what I mean is, so if you go to your very first slide, or the slide with the picture of the physical setup.
This one or this one?
The next one, yeah. Okay, so you suppose you've got a spherical bound. Is the boundary the machine or the boundary the object that you're scanning? Because you seem to be talking just then about the
well, I think you see this in this picture. You see how you should think of it. I mean, so you might want to measure a slice of the torso of this patient, and
I
so
see.
okay.
So what I had in my mind was more of an MRI scanner.
So it's not an MRI scan. So so the thing with electrical impedance tomography is that it is somehow you don't do kind of more like X-ray measurements, which is what you do when you do MRI scans, which have much higher resolution. But it's kind of crude. You can carry these electrodes in any ambulance, so you can make a quick test. So you don't expect this to image as precise as an MRI scan. It is sort of cheaper to create experiments. But of course, the fact that it's driven by electrostatics fundamentally shows that there's some price to pay in the recovery here, in the precision of the recovery.
Yes. Okay, all right, thanks. I think you've answered the question.
Okay, thank you very much. It's time we set up Hugo's talk. You're all going to find Richard if you Google for him and can drop him in another email with questions. I'm sure he's going to be happy to answer those. And so we have 2 minutes coffee break, enough for everybody to run to the kitchen. And now we change to Hugo. Thanks again, Richard.
Thank you. Thanks so much for listening.